Okay, let's solve another example on surface integrals. So we're still doing surface integrals. Remember, in the previous video, we solved the plane example. So we had this function, y axis z, we had this surface, we computed the surface integral of this function over this plane, and we found the flux, which was equal to half. So let's see now, for example, let's take the function as x squared y minus x z, and let's take the surface S to be all points such that x squared plus y squared equals 1c z between 0 and 2. Compute the surface integral of f dot and dA. Remember, okay, this is a surface integral, but basically this is the flux of f through the surface S. Okay. So the first thing, what is our surface? So our surface, it's composed of two equations. Let's say x squared plus y squared equals 1. That's a circle in R2. Because z is missing, we extend it in the z direction. So basically we get a cylinder, but the z is not free. You start at z equals 0, you end at z equals 2 only. This is our surface, and it's not a closed surface, so the cover and the bottom are open. This is my surface. The first thing, we need to find a parameterization. So what is the best parameterization for the cylinder? X squared plus y squared equals 1. That means we're dealing with cosine and sine, but it's not t. Now we're dealing with cosine u, sine u, and v is free, but the u values are between 0 and 2 pi. The v values are between 0 and 2, because the v represents the z values. So if we draw the u v axis, what are the values? The u is from 0 to 2 pi, the z or the v is from 0 to 2, so this is our domain. This is our domain. Okay, then we need to find r sub u cross r sub v. So this is I, j, k. R sub u, you differentiate the parameterization with respect to u. So that's minus sine u, cosine u, 0. R sub v, it's 0, 0, and 1. So if you compute what is the I component, it's cosine u. What is the j component? It is sine u. And what's the k? It is 0. So this is our normal vector. Then we're almost done. I mean, the rest is just standard computations. So the surface integral, it is the integral. If you go back to f, this is my function f, you replace every x with what you have in your parameterization. So every x is replaced by cosine u. So x squared becomes cosine square u. Then f, the y component, this is it, the y component is y minus x. You go to your parameterization, this is your parameterization, this is the y, this is the x. So you're saying sine u minus cosine u. Then the third component of the function f is z. So you take z from your parameterization, which is v. All of this you dot with the normal vector, which is r sub u cross r sub v. That's cosine u, sine u, and 0. du, dv. Again, we need to write the v limits, the u limits. What are the v limits? It's from 0 to 2. If you look at this, then for each of these v values, the u values are from 0 to 2 pi. And you do this integral. So this becomes the integral from 0 to 2, the integral from 0 to 2 pi, dot product cosine cube plus sine square minus sine u cosine u, the v with 0, du dv. Now this becomes the integral from 0 to 2, the integral from 0 to 2 pi. The cosine cube integral, if we integrate cosine cube, it will give 0, and I will explain this in details. And if you integrate this, it will give you 0. So the only remaining term is sine square. To integrate sine square, we need to write it as half 1 minus cosine 2u du dv, which is, this is the half, integral from 0 to 2. The 1 gives you 2 pi, and again the cosine will give you 0. When you integrate the cosine, you get sine. After substituting the upper limit minus the lower limit, you get 0 dv, and this is just 2 pi. So the final answer is 2 pi. Again, we look at this as the flux of our function through this surface, the cylinder. Okay, so let's, as a comment for the computations. So in our computations, we mentioned that the integral of cosine cube, the integral of cosine cube u du, we mentioned this is equal to 0. Why is it equal to 0 quickly? We can do it in details like in calculus, but quickly, if we draw the cosine function, it starts here, it goes back, then it goes up. This is here 2 pi, this is pi over 2, this is pi, and we know that for sure that this region as areas is exactly equal to this, and this region here is exactly equal to this. So basically, if you integrate the cosine, it will be 0. But what happens when you cube this? So if this is raised to the power 3, what happens? The positive curve, this is a positive curve. When you cube it, you will have a positive curve. This is negative curve. When you cube it, you'll have negative. Negative stays negative. Positive stays positive. So basically, okay, the shape will be different, but the positive quantity will remain positive, the negative quantity will remain negative. So when you integrate from 0 to 2 pi, you have this is a positive value, which is exactly equal to this, but with a negative sign. So when you integrate the first region with the second region, they get cancelled. This region with that region, they get cancelled, and you get 0. So this is the quick explanation why the integral of cosine cube is equal to 0. The other justification, because we need these understandings for future examples. When you do the integral from 0 to 2 pi cosine cube u du, basically, if you want to do the integral, you will need to do some techniques from calculus too. So basically, this is like 0 to 2 pi, you write it as cosine u, then cosine square, which is 1 minus sine square u du. After that, you need to substitute, so these are the details. You substitute the sine u as x, for example, which means cosine u du is dx, du is dx over the cosine. So this becomes cosine u 1 minus x square dx over cosine u. But this time, the 0 and the 2 pi, we need to be very careful that these are the u limits, not the x limits. And we need to be very careful that we can't, usually when we do integrals, we say, okay, when u is 0, then x is 0 through this substitution. And when u is 2 pi, then x is 0. So if you want to change these limits and write them as from 0 to 0, that's wrong. The reason for this mistake, we can't write from 0 to 0, although the final answer would be right, 0, but we don't write it because the substitution theorem, it allows you to substitute as long as the function is 1 to 1. So if you substitute the lower limit and the upper limit in your substitution and you get the same value, don't do it. That's wrong. You can't do it. So I'm keeping the u for my reference. So the u is from 0 to 2 pi, the cosine is cancelled, 1 dx, so that's x, minus x cubed over 3 d, so this is after integration you get x minus x cubed over 3 from u 0 to 2 pi. So if you go back to the u, what is u? You replace it by, so the x is sine u minus sine cube u over 3, and now you substitute the 0 and 2 pi to get 0. So these are the details of why the integral of cosine cubed equal to 0. Again, instead of doing all of these computations, we can do it just this quick way. The other integral that we mentioned in our computations here is why the integral, so I need to explain why the integral from 0 to 2 pi sine u cosine u du equal to 0. Again, you can do it quickly using substitution and it will give you 0. But I like to explain this geometrically because the sine cosine, both functions, they are periodic. They repeat themselves. Again, I need these ideas for later examples. So this is the sine function. This is the cosine function. Roughly, of course. So this is the cosine. This is the sine. The idea, instead of drawing them from 0 to 2 pi, why not looking at these two functions, because they repeat themselves. So I can look at them from negative pi to pi, any interval of length, 2 pi is enough. So this is the sine, this is the sine, which is an odd function, and this is the cosine, which is an even function. So the idea now, I can look at this integral as the product of an odd function with an even function, but as the integral from negative pi to positive pi. And we know that when you multiply an odd with an even function, you get an odd function, and the integral of any odd function from negative pi to pi is 0. Again, you can do it as in calculus, but these geometric interpretations are needed later in even other chapters. So in the end, we computed the integral over this cylinder, and the answer was 2 pi, and these are the details.